sample exam 6, 29 through 37. And number 29, we have a continuous function. It says let f be a continuous function such that the integral from 2 to 3 of f of 2x dx is equal to 8. And ultimately what we want to know is what's the value of the integral from 6 to 4, or 4 to 6 I should say, of f of x dx. So ultimately, if we look at the integral that we're given, we know that this is equal to 8, it says. And with the, I guess what we could consider here is knowing that it's a composition here. If we try to do a u substitution with that, our du here would be 2 dx. Okay. All right. And if we change it as such, we'll have our 1/2 du be our dx, and if we substitute our f of u, and we'd have 1/2 du out here. Okay. So keep that in mind that that would be our integral. I didn't put the limits on there yet, but if we did write this integral in u, we could change our limits accordingly, according to u, if you will. We'd have a 4 here and a 6 here. True. And so, like I said, with the information that we have at this point is that this integral right here, the one that I started with, is ultimately the same as that right there. Do you agree? True. Okay. Because if we were to solve this integral, whatever that f function was, let's just say for argument's sake that it was sine of 2x, okay, we would do exactly that. We would put the u equals, and then we would figure out our du, do the substitution properly, and we would get this new integral that looks like this. Okay. All right. Now, ultimately, like I said, if these two equal each other, then wouldn't this also equal 8 then? Wouldn't that be true as well? And if that equals 8, then wouldn't this equal 16? And ultimately, whatever my variable here is for f, the function isn't different whether I have u as my independent variable or x as my independent variable. So really, ultimately, this right here, which we're looking for, is right here, isn't it? And therefore, we get 16, which corresponds to the letter D. All right. Now, another way to think about that may be maybe not so much the limit parts, but when we multiply 2 by our function or by our x values, remember that creates a horizontal stretch, if you will. We're multiplying our x values by 2. So would it be surprising if we stretch this function that we get a bigger area, if you will? So you can think of it in the context of stretches and shrinks as well, but like I said, the better part would be to use calculus and make sure that we actually get the actual 16 in this case. What else? 29 through 33. Right? 33 says we have the density. Going back, that would be a AV problem. U substitution. All right. We have the density, which we, you remember we call that variable rho. And it's measured in grams per meter. So the question here says the density of a thin metal rod 1 meter long at a distance x meters from one end is given by the rho equation, and the question is what is the mass in grams of this rod? Okay. So again, this is the density function. Notice that it's essentially a rate function, if you will. It's grams per meter. The context like meters per second, like a rate we think of like that, but it's ultimately a function that has a division as its units, grams per meter. And so think about would it be just a straight integral here? If I were to draw a picture of rho and find an area of a rectangle, rho here is measured in grams per meter, and x is measured in meters. And so ultimately, if I did find that area of that rectangle, I would have grams per meters times meters, which would give me grams, wouldn't it? So we would in fact get grams if we did the integral of rho. What about the limits here though? How long is this object? It's just 1 meter, isn't it? Then we go from 0 to 1 meter. Because ultimately it says this is measured in x meters from one end of the object. So if we calculate, we have our integral of 1 plus we get 1 1/3, which corresponds to letter B. Well, that would be a AB problem also, just an integral as an accumulator. Questions on that one? Others? First 4? Okay. Second half, 34 to 37? Okay. 35, we have says a missile rises vertically from a point that says from a point on the ground 75,000 feet from the radar station. So ultimately, here's your radar station, we'll call it R. Here's the launch site, we'll call it M for missile, I guess. And ultimately, that distance right there is 75,000 feet. And it says that the missile is rising at a rate of 16,500 feet per minute, so the missile is going up, so this is a variable quantity. I'm going to call it y because it's in the y direction. So this variable y here, that's changing. And it says that the missile is rising at that rate, which ultimately is a dy dt, 16,500 feet per minute. Feet is the measure of y. T is the measure of time here. Feet and minutes are what we're given. And this is at the instant when it's 38,000 feet high. What is the rate of change in radians per minute of the missile's angle of elevation from the radar station at that point? So ultimately, keeping in mind that, we can call that z because that's a changing quantity also. We can call this theta because that's a changing quantity. As the missile goes up, the angle is going to change. That is the angle of elevation in question. So with that said, we're ultimately just after d theta dt. We want to know how is that angle changing at a particular instant. So this is a very typical AB problem of the topic related rates, which our general strategy for that is to draw a picture, identify all our variables, all our constants and variables, figure out what we're looking for in terms of a derivative here. So they're looking for a change in quantity. And then from there we write an equation that relates our variables. Well, in this particular case, can I write tangent theta equals y over 75,000? Would that be a valid equation in this picture? Right, and from there we can, once we get that to that point, we can differentiate with respect to time. And so we get secant squared theta d theta dt, which introduces the variable that we're looking for. There's our d theta dt. And then over here we'd have 1 over 75,000 dy dt. Again, our 75,000. It's just a constant, 1 over 75,000. Y's derivative is 1 dy dt. And conveniently we know dy dt, and so the only thing that we don't know here at this point is theta. Because over here we'd have 16,500 times 1 over 75,000. So simplify it all at the end, but ultimately that's our stuff on the right hand side. On the left again, we just need to know theta. Well, here's where we use the instant. Remember they told us that the instant is when the tangent theta would equal when the rocket's 38,000 feet high. So if we figure out the theta at that point, we know y at that point, we need to know theta at that point. So ultimately our theta is going to be tangent inverse of that stuff. So 38,000, I'm just going to do 38 over 75, just get the zeros. So we get to 0.4689666, etc. I'm going to store that because I'm going to use that over here in a minute. So always do the storing part so that we don't have to retype that in and get a rounded answer that's not correct. So ultimately our theta is that. So I'm just going to call it A at this point because I stored this in A. Alright, so the next issue is how do we find d theta dt? Well, all we have to do is take that quantity and we're going to divide it by sine squared or secant squared of A. True? So why don't we get that quantity? Let's get secant squared of A in our calculator. So we know secant squared is 1 over cosine squared. So if we do cosine of A, which we still have A in there, so you can just go cosine answer. Square that. Right. So there's your cosine squared of A, and we want 1 divided by that. So there's our secant squared of A right there. And all we're doing is dividing that into 16.5 divided by 75,000. We're taking that, we're dividing it by our previous answer. So I really didn't have to store it, but ultimately we get 0.175. Should correspond to letter A. And the units on here would be radians per minute. Questions on any of those parts? What else? Let's take a look. Says that we have f of x here is a function whose Taylor series converges for all x. And it says that if the y value of the nth derivative is less than 1, where f of n, f to the n of x is the nth derivative, the question is what is the minimum number of terms of the Taylor series, okay, centered at x equals 1, necessary to approximate f of 1.2. I think that's supposed to be a point, not a comma. I assume a comma wouldn't make sense there. And it says with an error less than 0.0001. Alright. So ultimately it's our remainder estimation theorem situation. Okay. So it makes it a BC problem right off the bat. So alright. So we know that that our remainder here is going to involve this m value that we know, remember, is the maximum value of the nth derivative, or the n plus 1th derivative, I should say. And the knowing that the absolute value of the nth derivative, okay, keep in mind that the fn notation right there, that's going to be the y values of the nth derivative, if you will. Okay. And knowing that they're going to be less than 1 here, okay, if they are less than 1, then our m value here is going to be that or something different. What do we say? If that value is less than 1, remember in general we want this m, and keep in mind that it's going to be x to the n plus 1 over n factorial. Alright, so let's deal with that in a minute, but let's go with the other part here first. We got, again, we're approximating the interval here. We're going from 1 to 1.2. Right? So ultimately my 0.2 is going to be my x value here. Remember, we want this to be less than 0.00001. Alright, so let's say for argument's sake that we're going to let that m just be 1 here. again, the maximum value of the nth derivative is going to be less than 1. Okay. If it were 1, then ultimately this would be our equation. And again, the number of terms here, if we let the number of terms be either 3, 4, 5, 6, or 7 are our choices here, let's decide what, let's start with a 3. Keep in mind if we had 3 terms, if our n were 3, we would have 0.2. We'd have this to the 4th, and then over 4 factorial. Actually, I think this is n plus 1 factorial, isn't it? So let's see what happens if we do that. If we do 0.2, we raise that to the 4th. We divide that by 4 factorial. We get 0.00007 essentially, rounded. Okay. Which ultimately, how does that compare with this one? Remember, we want the error to be less than this. This is actually bigger than that. Okay. So that would not work. Alright, and then let's try, if we tried 4, then we would have 5 in there, so we'd ultimately do 0.2 to the 5th. And we divide that by 120, 5 factorial. So that would be, if we did the 5, we'd have 0.00003 ultimately, which again would be too big. So let's try it with the next one, which is 5. If we had a 5, 5th term would be, the n here being 5 would give us 6 as our power in factorial. 6, divide that by 720, 6 factorial. Now we'd have 0.00000. It's like 7 of those, right? 9. Okay. And ultimately, once we got to that term, now our error is less than that 0.00001. Okay. So the error here would not be, and the error once we got to that 5th term, if you will, where the n value would be 5. Okay. Again, giving that n, that would be our 6 power, 6 factorial. That would give us something that is less than 0.0001, and so therefore that would be the correct choice. This one, again, that would be when n equals 5, so it should be C. Alright. So keeping in mind that without knowing the actual function, would there be really any way we could find an actual m value here unless they told us something about that m? Okay, them telling us that it's less than 1, keep in mind that if it's less than 1, if this were less than 1, then wouldn't the error here, the error that we calculated, be even less than this? Okay. We can't, you know, this is basically as big as the error could be, isn't it, if we let m be 1? Yeah, if we said m was a half, this would be even lesser, wouldn't it? Okay. But do we know that m is a half? All we know is that it's less than 1. So if we go worst case scenario, then m is 1. Right? That's going to give us the most error if m was 1. If m was anything less than 1, then the error is going to be even lesser. Alright. Others?